In today's lesson, we will be discussing the various properties of water that make it one of the most important substances on the planet. Before we get started, the most important thing you should remember while participating in this activity, or these series of activities, is that water molecules are polar molecules. You forgot? Well, here's a little review. The reason that water is a polar molecule is because of an uneven distribution of the electrons between the oxygen and hydrogen atoms in water. Since oxygen is a much larger atom, it attracts the electron more than the hydrogen atom. So the electrons spend more time around the oxygen atom. This creates a positive dipole on the hydrogen atom and a negative dipole on the oxygen atom. Another easy way to calculate whether or not a molecule has dipoles is through the difference in electronegativities. If the difference is between 0.4 and 1.4, then the bond is considered polar. If hydrogen and oxygen had the same electronegativities, then there will be no dipole moments and water will be a non-polar molecule because their difference will be zero. Now that you know the basics, let's start with something simple. We have to be able to find the volume that one drop of water occupies. This is easy, as we just have to count how many drops of water it would take to fill 1 milliliter in the graduated cylinder, and then we do simple division. The results show that one drop of water is about 0.0667 cubic centimeters. Not bad. Now let's move on. In our first activity, we'll find how many drops of water can be held on a penny. This is a wonderful experiment that will allow us to test just how powerful hydrogen bonding is. Using prior knowledge, we know that hydrogen bonding is a result of the water molecules being polar. In normal water, there's nothing to interfere with the hydrogen bonding. However, in salt water, the water will naturally bond with the sodium and the chloride ions, replacing the hydrogen bonds with ionic bonds, well, most of the hydrogen bonds with ionic bonds. And it's because of this that we can predict that there will be more drops of normal water molecules on the penny than salt water molecules. As we can see from the table, our prediction was affirmed, as about 1.967 cubic centimeters of normal water was held on the penny, while only 1.4007 cubic centimeters of salt water was held on the exact same penny. Now, as a little bonus activity, let's see what happens when we rub detergent on the penny and repeat the experiment. Well, we see that the detergent greatly reduces the number of water drops that can be held on the penny, as there were only 0.7114 cubic centimeters of normal water and 0.3335 cubic centimeters of salt water on the penny after the penny was rubbed with detergent. And that is a great decrease. Now, this little bonus experiment, demonstrates how detergents work. Detergents have a hydrophobic and hydrophilic components. Based on this principle that like dissolves like, the hydrophobic components love to attract to grease and oil, while the hydrophilic components love to attract to water molecules. This allows detergents to bind to the grease and oil on your skin or whatever, and be washed away as they bind to the water molecules. Great, now that we're done this, let's move on. In this next section, we will be taking a look at the adhesive properties of water, by observing the forms that water makes on different surfaces. Now, on first sight, we may predict that the water will form equal dome shapes on all the materials. However, we have to keep in mind of water's polar nature, which affects how strongly the water binds to the material. The three materials we'll be using are a penny, a glass slide, and wax paper. As we can see from the results, the water forms the biggest dome on the wax paper, and it forms the flattest dome on the glass slide. The reason for this is polarity. Wax paper is made of a non-polar substance. Since polar and non-polar molecules don't have any interactions, the water molecules are forced on top of one another, creating more hydrogen bonds and causing the higher dome. Glass, on the other hand, is a polar substance, which causes several of the water molecules to become attracted to the glass. This is the reason for the flatter dome, because the water molecules are spread out and want to form dipole bonds with the glass, resulting in less hydrogen bonds. The penny is also slightly polar, which is why it forms a medium dome somewhere in between. Okay, so how does this activity possibly connect to real life? Well, take a look at a water strider. It's a type of bug. You see, their legs are coated with a hydrophobic substance, and this allows them to be able to float on water, as the water molecules, which are polar, will not bind or attract to the coating substance, which is nonpolar. This is shown with the wax paper in the water, as the wax paper doesn't bind with the water, and it causes the water to create a big dome shape, meaning that there's resistance, there's no attraction between the water and the wax paper. This essentially allows the water strider, which is also very light, to traverse lakes and ponds with ease and without drowning. But if their legs were coated with a substance that was, let's say, hydrophilic, then the water molecules would bind with their legs and then they would sink. This is demonstrated with the water and the glass slide, as the water there doesn't create that nice dome shape as the water is attracted to the glass. For our last experiment, we will be analyzing the effects of water using paper chromatography. In this activity, you will be using a marker and you will place a single dot on the chromatography paper as shown. Then you will place the paper into a beaker so that only a small portion of the chromatography paper is touching the water and is not touching the dot. Then you shall observe. This is a table that shows how far the water traveled in time intervals. The water reached the top of the chromatography paper at the end of 39 minutes and it traveled 70 milliliters. It started out at 15 milliliters and in 5 minutes afterwards it reached 34 milliliters, then 47, then 53, then 59, and so on and so forth. So if you pay close attention, well, not that much, it's pretty evident. If you looked at the chromatography paper after, let's say, like 10 minutes, 5 minutes, you would see that the solid dot, the solid black dot, has changed into a wide range of colors. And the reason for this is because of the different chemicals that make up the marker. You see, every chemical has a different polarity and consequently a different solubility in water. As the chromatography paper absorbs the water will transport all the chemicals up the chromatography paper. However, the chemicals that are more soluble in water will hang on longer and travel farther up the chromatography paper, while the chemicals that are less soluble will be found further down the chromatography paper. This explains the separation of all the colors, because there are different chemicals that go into a marker. Okay, in this final activity, we will talk about the physical properties of water. As you can see, I've gone through all the trouble of getting and organizing the data, so it should be easy from here to analyze it. As we can see from the graph, the ice melts at 0 degrees Celsius. Why? Well, if you look at the graph, there is a slope of 0 at that point, because the substance stays at 0 degrees for 3 minutes. Now, using the same logic, water boils at 100 degrees Celsius because it stays at that temperature for 7 minutes. Well, you may be asking, well, that doesn't really explain much. Okay, well, let me provide further explanation. You see, the temperature of the water doesn't change while the ice is melting or the water is boiling because the heat absorbed by the water is being used to change the state of the water. This is called a phase change. Before this change, the heat is absorbed by the molecule to increase its temperature by increasing its average kinetic energy. However, there reaches a point where the substance can no longer hold its state, so it absorbs the energy to break its intermolecular bonds rather than use that energy to change its temperature. And this is when the phase change occurs, and it explains why the substance doesn't change temperature during this phase change. Now, water's high specific heat is very useful in our lives and has many applications. For one, it keeps the land around a body of water cooler during the summer and warmer during the winter. This is because it takes a lot of energy to warm a body of water. So during the summer months, the water gives off cold air currents while it's being heated up. In addition, it also takes longer for water to lose that heat energy. So during the winter months, the water is still pretty warm compared to the surrounding air. So the water gives off warm air currents which heats the land. Another usefulness for water's specific heat is its ability to preserve fruit during cold nights. Now, sometimes farmers who grow like oranges or apples, when they hear that there's going to be a cold night, they throw water on their fruit. Now, why? Well, this is because during cold nights, the water will essentially lose most of its heat energy, and it will take most of the cold chill at night. Now, this is the reason why in the morning after a cold chill, fruits will be covered in icicles, but the fruit is unharmed, because the water will take all that energy, will lose all that energy to turn into ice, and it will protect the fruit from losing its moisture. Thirdly, water's high specific heat capacity also allows it to be used as a useful coolant. Now, in machinery, a lot of heat is produced, such as in your computer or in nuclear factories. Now, this amount of heat energy in high amounts is very dangerous, as it can cause damage to the environment or the equipment. Water is used because it can absorb a lot of heat, because in order to raise 1 gram of water by 1 degree Celsius, it requires 4.12 kilojoules. That's a lot of energy, and that's why water is a very useful coolant in this case. Now you're an expert on water, but how does this affect real life? How is it applied? Well, the most common and evident application of water, of these properties of water, is seen perfectly in plants. If you look at a tree, now most trees are usually several meters above the earth, 20 meters, 10 meters above the earth. So how does water manage to reach from the bottom of the roots all the way to the leaves at the very top? The answer, of course, is found in the water. You see, plants, much like humans, have to breathe. There's a section in their photosynthesis where they must inhale and exhale in sort of the same fashion as we do. Because of this, when the plant exhales, some water molecules escape, and some water molecules also evaporate. But every water molecule isn't alone. You see, as we learned, since water molecules love to form hydrogen bonds, when one water molecule leaves the tree, it essentially pulls on the water molecule behind it through its bonds, and that water molecule pulls on the molecule behind it, and so on and so forth. This essentially allows a whole chain of water molecules to be pulled from the roots all the way to the top of the tree, as the water molecules evaporate or leave the tree. Along the way, the water molecules are distributed to the other cells in the tree, and this is how water reaches the other extremities of the plant or the tree from the roots, from the ground. However, there is also a conundrum, shall we say, for the plants in this case. You see, on the surface of leaves, there are openings called stomata, and these allow gas to flow in and out of the plant. However, when the stomata opens to allow the gas exchange portion of photosynthesis to happen, a lot of water is lost, as we have seen, because not one molecule of water escapes, but a whole chain of water molecules escape. So although the properties of water do allow water to reach nearly any part of the plant, no matter how far it is away from the roots, it also causes a huge loss of water when the plant undergoes photosynthesis. And this is in itself a very big problem.